All right, Huamin, go for it.
Sure, thank you. So I'm from the accelerator enablement team. And my name is Hua Ming. Mostly working for Meta internal server side inference workstream. And the problem we are seeing is trying to adapt to PT2, right? With torch export, with IoT inductor. And so what we were told previously is, oh, like given a single model, don't do anything like symbolic trace and don't do anything like what we have for ACC tracer, but just directly run torch export. So this is the recommendation. And but like in reality, what we have is the model we are running, it just coming natively with some legacy quantization APIs. And this usually means torch export will fail. It's like with various issues. So like for two specific quantization API, one is the FP16 dynamic Q linear, and the other is just the int8 Q linear. Um, I think the reason they are getting failed is, is using the old school or like legacy quantization API, and PD2 just does not support us natively. So my question would be like, how do we deal this kind of situation? We do have some offline discussion, but I think this might be like a good opportunity to expose the issue here.
Okay. Anyone want to jump in? Say a little bit about the offline discussion. Otherwise, I'll start asking questions.
And I can share a bit more context
Yeah, go
on
for it.
like L's plan for supporting like all these quantization passes. So there are essentially two quantization passes in consideration. So the first one is the legacy one, which first you FX symbolic trace into a graph, and then you do some graph passes to introduce the legacy tensor and legacy quantization ops. This is currently happening before the export. So in the export, when the graph passing the export have this unexportable part, that's why Huamin run into this export issue. The legacy quantized tensor are not fakified and thus not exportable. And legacy quantized ops are not lowerable by inductor. So even if they are exportable, they are not compilable. So that's legacy path, quantization path. The new quantization path that AO team suggested is called PT2E, which is a torch exported based quantization. So first you torch export to get a graph, and then you run PT2E quantization to introduce the QDQ pattern, and then you do some pattern matching to turn that into one DNN up that was backed by an actual quantization kernel. So we had conversation with Jerry, and then that's our plan forward. So basically, we're gonna move the quantization passes after the export so that we can use the PT2E new quantized pass. But there are work implied. Basically, all those 23 quantized operator that show up in the production model today needs to be covered by the PT2E workflow. And all those 23 equivalent like quantized operator need to have a lowerable pass in AOTI if we wish to compile it. Yeah.
Okay, that sounds like a plan. Are there any questions, comments from the room about this plan? Huamin, I have a question for you, which is, this amount of work is fine. Like, there's not a timeline problem or anything like that. Like, you can actually take the time to just port these to the new quantization framework.
Um, so this is a long-term plan. So we plan to, I mean, we do have some short-term plan to make this mitigation by the end of the half. So which is like we do have some pre-pass things before torch export, and what Sherlock mentioned is gonna be starting next year, so like H1 next year.
Tell me about
Yeah,
the
and
short-term
then
mitigation. What's the plan for the
yeah.
short-term mitigation?
So short-term mitigation is mostly about this two quantization linear APIs I was mentioning about. So like uh we are trying to introduce some wrapper uh linear op to bypass like the torch exports issue, and otherwise like it will just fail with quantization non support or blah blah blah. Like I think it's in Dynamo, and so once we have this wrapper op to bypass the torch export, in AOT inductor, like we will decompose this wrapper op into two sub op. The first one is taking care of the, like for linear, we do have to use the package weight. We need to decompose it to the packet weight, and we got the packet weight as like a constant in the graph. And then the next one we decompose is the real Q linear things, which we will just use this constant as a packet weight to run linear in forward.
Okay, that sounds like work. Do you know if this is going to work, or is this sort of in development, or what?
This already works, and it's basically just like to bypass whatever issue we are facing, like in the torch exports for AOT inductor, but underlying we are still using the legacy quantization PIs.
Okay.
And the reason why we can take this path is we're only targeting one model, which has two ops. So we can write passes specifically for those two operators. But like I wonder if this is probably not gonna be scalable when we scroll out to more models. Yeah. So but like for the model that we target this half, which only has these two op, we're gonna move forward with this workaround.
Okay. So getting on the new quantization API is great long term, as long as you don't end up onboarding more models in this way. The short-term fix also seems fine. Any other questions, comments from the room? Otherwise, thank you for telling us about this.
Well, one thing that I was just say like follow-up investigation is like what is the PD2E's coverage for those 23 context ops? I don't know yet. Like I think we'll need like Jerry and AO teams help to help us like investigate
I see Jerry
or
and others here. Do you want to comment on that?
Yeah, yeah, I can quickly comment. So like I think so right now the CPU X like Intel, like there's a like for CPU backend there's an Intel x86 inductor backend that supports mostly linear and conv, I think, plus like maybe some fusions. For the rest, I don't think we have support in that backend. So, but I think the supporting in quantization flow itself is not so much. Like we just define some configurations, and the main work will just be like implementing the ops and also the lowering passing inductor.
Okay, so quantization folks, you all have agreed that you're going to have this ready in time for next half?
I don't think we have people working on this right now.
Okay, so sounds like there's still a staffing question here.
Yeah.
Yep.
Okay, thank you. All right, let's move on to the second topic. Eeny, meeny, miny, mo. Let's talk about Apple Silicon. Let's see. I don't know. We've got Albin here. Yeah, Albin, why don't you kick off the discuss?
Sure. I think Apple Silicon is an interesting backend we've been looking at for some time. I think there are quite a few moving pieces and quite a lot of history there because I think we've been trying to get, at least on Mac OS, an accelerated Apple backend for the past 4 years. I don't know if you remember, Ed, you were in these first discussions. But so there's a lot of things that happen. I think the two main questions we have at the moment are trying to understand exactly how much do we care as the PyTorch team about Apple Silicon, and how much we want to, I would say, invest ourselves into that, and how much we want to just collaborate with the Apple team to make sure that happens. And also, we are trying to discuss all the different work streams that are involved and that are going to rely on that MPS backend to make sure that we do everything that is necessary so that these work streams can work the way they need to. Is that a good intro?
Sure. Let's see. Do we have a Horus in the room? I do not see a Horus. Do we have someone from TorchTune in the room? I clearly need to add more invitees to this meeting. Let me think. Okay. Any comments, questions from folks generally? All right, I'm going to call on someone who upvoted this topic. Mark Seraphim, can you tell us about some answers to some of the questions Alvin posed? Do we have a Mark Seraphim? Actually, don't see him on the invite list. All right, moving next to the list. Driss, give your take on Alvin's questions.
I thought Albin's first question, how much do we care about Apple Silicon, was a good maybe question for the group. I don't know, do we expect people to train actual models that are used by people somewhere on their laptops or Mac Studios? Or is this a pure inference Llama CPP thing?
I think it's a good question. As an anecdotal data point, Ed sent me some Twitter post from someone that was like, it's amazing. You can actually train pretty large models if you have a beefy M3 MacBook with a single machine. So I think there is some anecdotal use of training. I think inference, I would agree, or I would expect, is more interesting.
I
Jake?
thought they back for like fine tuning, if that's what you meant by training.
That particular example was actually training. I think fine tuning is there as well. Yes.
Jake?
Yeah, I was gonna say for students, this seems like it would be pretty useful from like the hobbyist space. I don't know like what the kind of marginal gain is over having everyone in like a college use Google Colab versus their local MacBooks or something, but it seems like being able to run things locally and stuff and not be beholden to your Google budget seems pretty good.
Alvin, do you have on hand like performance numbers about like how, for example, how many batches like per second you reasonably would expect to be able to do on popular model architectures on like an M3?
No, I do not have that on hand. Nikita is the one that has been looking at performance from Torch chat side. And so on that side, they do have some numbers if you're interested.
Do we have a sense about the market size? How many people might be blocked on that? How big a deal it is? Alban, do you know?
No, I think it's part of one of these ethereal questions of like, I think if you look at the overall market size, Mac OS is not that big, but at the same time, our crowd is very biased toward MacBooks due to various reasons. So they have MacBooks. Whether they are actually interested in running things locally or not is another question. So I think there are a lot of unknowns, and I don't think we have a good answer. No.
Is there a forum we can ask this question and see how people are interested in it?
I think we have some signal in that sense of like, you know, our GitHub issue for adding more coverage to MPS is the most commented issue. I think the issue asking for MPS support was one of the top ranked issue as well in terms of like reactions to it and people being excited about it. I think the initial launch that was 2 years ago at this point, I think it was pretty successful and was picked up pretty big. So I think the hobbyist community seems to be very interested about that. I think we are struggling a little bit to measure exactly what's the actual impact there.
Do you have other questions, comments from the room? Yes, MPK.
Yeah, I guess I'm curious, like, on the PyTorch side, what are people working on? Like, I hear there's a Torch Tune or other people working on MPS stuff.
Edge has like an MPS delegate, but we don't. We go through a different system than like the device that Core would use.
Actually, can you tell us a little more about that delegate? Is that using the MLX stuff or something else? CoreML?
I don't know. I could get someone else to comment. Well, CoreML is separate. We have two different Apple delegates, CoreML and MPS.
So I can answer that actually. So nothing goes through MLX, basically, Ed. And I think MLX is more of a ground-up framework that is purely based on Metal, that we have very little interaction with. We did chat with them. We did collaborate on some of the low-level Metal kernels with them, and that has been happening, but there is no specific interaction there. On the executor side, there are two delegates, one that is MPS, one that is CoreML. And both of these are built, like all the other delegates, through collaboration with the company, the corresponding company. In this case, both of these are built with collaboration at Apple, but two different orgs within Apple. So one on the mobile side is collaborating on CoreML, and one on the GPU side is collaborating on MPS. Because they are different software solutions, they support different things, work at slightly different levels, so they have slightly different characteristics.
Okay.
And in terms of what Core is working on, I think we're mainly working on the stability of the backend. Like, we're mostly supporting basically the Apple team that is staffed to work on this, where the main objectives are stability of the backend, long-term performance through compile, and short-term enablement of high-profile models in their programs.
Yes, hand. Just.
I was just looking back at the like post that incited this all. It seems like fine tuning is like a realistic workflow or workload for doing stuff on your local machine. Torch Tune, I mean, it says they don't have MPS support. It's coming at different like, do we know why Torch Tune, like our solution to fine tuning, doesn't work? Like, why can't you just do set default device MPS?
My expectation is it's a mix of, well, I don't know how much it does not work versus it partially works, and so we prefer to say it doesn't. My expectation, I think it's a mix of two things. One, the stability problem of the MPS backend in Core, like the things that we look at do work, but a lot of other things do not. And so by default, a lot of things just don't if you do funky stuff. And two, I think, is the state of our, what I would call device generic APIs, where today, if you build something pretty advanced like Torch Tune, you're very likely to, by chance or by choice, hard code some torch.cuda APIs and stuff like that are just not going to work with other devices. And you basically need someone to sit down and like spend a whole bunch of time to enable that repo for other backends.
Jane?
Yeah, to add, I was saying I've been like working in TorchTune a bit, and it is the problem of like everyone in TorchTune is optimizing for CUDA essentially. And I think Vincent had already commented on the thread, like something like pin memory equals true. Certain APIs are just not like supported in MPS, and there's just no like testing for it. So even if a bunch of ops should work just because they're composite explicit, I think there are quite a lot of optimizations that are very CUDA heavy in TorchTune. I guess the question I had following up from this is just like, how much of this post is about, hey, we should be more conscious of MPS/metal. I don't really get the distinction between the two in like development and optimizing for those use cases versus like how much of it is MPS coverage support in core versus, hey, for everything we're building on top of core, we should test on CUDA and MPS, which I don't think is happening much.
Do we have anything from Devinfra here?
I would definitely agree with that statement. I think the AO library, I don't know if Mark is here, but I think AO is in a similar situation where, as of today, they are focusing on CUDA, at least until PTC. But I think, yeah, I would definitely agree that there is a non-core part to that question where when we build these tools, we need to be conscious about not only CUDA, but other backends, if we are to say that these other backends do matter.
Okay, I might revive this topic when I have more people here. I see a connection to Devinfra and like OSX testing capacity and MPS testing capacity. I see a connection to TorchTune where, thanks Jane for repping TorchTune, but like, well, yeah, I need reps from TorchTune. Albin.
I'm not convinced Dev Infra is really involved here. I think we do have capacity.
Okay, so basically, if I did want to set up MPS tests, then it would be easy to do so. Vincent.
We have capacity, we have runners, we have the generic C infrastructure to run tests in MPS. So I don't expect it is a blocker that, Infra needs to be building something
new. Vincent?
Yeah, maybe, sharing some of the vibes I got from TorchRL users. So RL, usually we have like shallow models, things that you can easily execute on your computer, on your laptop. And so a lot of users are trying to do that. And the opportunity with MPS is really big, because like you can scale things very easily without relying on a cluster. And what I got from users is most of the time they try, to call something .mps and they hope it's going to work. And either they encounter a silent bug or an explicit bug, and then they're like, well, this thing is just broken. So they come back to me and I say, well, this is not TorchRL. This is like just MPS backend that's broken. And then they never come back. So what I'm trying to say here is, if we're looking at adoption and opportunity, we should probably not only look at who's actually using it right now, because a lot of people probably have tried and then went back and just say, well, I'm not going to pursue that route. There's, I think, an opportunity of fixing things and then, having something that really works, which is not the case right now, in my opinion.
Vincent, would you say it is bad enough that a rebrand would be necessary, or do you think people would be willing to try again if we told them?
Yeah, so I'm biased towards my user base, but when people do things like copying from CPU to MPS and then back MPS to CPU and all these kind of things, like there's always something that breaks, and it makes really the feature, at least in our case, unusable. So right now, if someone tells me I'm trying to use MPS to do something, I usually tell them, don't do it. Like, just do not go down that route and try to do things either on CPU or on CUDA, but just forget about MPS for now.
Okay. Any other comments, questions? Otherwise, I want to close up this topic.
I have a quick question about the hardware, just because I don't run Mac. I'm a Linux person. my understanding is the memory is shared between the metal and the CPU. And so does that mean that we could do like a more like mixed execution where we do like matmuls using the metal hardware, but then everything else using the CPU backend, or is it less flexible than that?
I would say technically, yes, you can. You will need to do synchronization very carefully because these two part of the dies are not synchronized naturally. But technically, yes, I think you can do that.
I did notice that when I looked at GGML and TinyGrad, they were often saying it was both metal and accelerate, right? They just wanted to use the stuff that was available, and that includes the CPU cores as well.
I think Accelerate will use the GPU and the A&E when appropriate as well.
Oh, really? Because I Googled Accelerate and it was like, it's for doing vectorized CPU.
And another question in that is for memory bound operations, will the metal hardware have higher memory bandwidth than the CPU hardware, or does it make zero sense to actually offload memory bound stuff to the GPU hardware?
I know the overall memory bandwidth is much worse than the CUDA GPU one. I do not know if there's a difference between the CPU side and the GPU side.
These all seem like great questions. Driss.
Yeah, sorry, one last question. Does that like unified memory model just not jive with PyTorch's assumptions on how we do things? Like, is MLX uniquely suited to make a better framework with the understanding that the unified memory model is like core to the things they're programming for?
I would say if you asked a year ago, I would say yes, but now we have copy on the right, and I think we actually can do very cool stuff. Which, one thing that I would say, by the way, is that I do share some of the frustration on like there are all these cool things we could try and do, and we haven't been able to. So I think exploring more kernel designs, unified memory are the kind of things that we've been discussing for past year or so. So yeah, these are all great questions and indeed things that we would like to see happening.
All right, thanks everyone for the lively discussion. I think we're gonna need to talk about this some more. All right, I'm gonna move on to the next topic. This one's me, I guess. Let's talk about VLLM inductor compilation. So I have a thing to share. Just a moment. All right, so this is about a recent discussion that Horace and I were having with some folks on VLLM. I'll first briefly go over this doc in case you haven't read it yet. So the basic concept here is that VLLM is a inference-oriented solution, and they want stuff to run fast, and they want to like optimize things, and they also don't want the startup time for their engine to take too long, because there's lots of cases where you are starting from scratch, and so warm-up time is bad in this case. And so we've been talking to them about like the stuff they've been doing with Torch Compile, and there are a few things that emerge. So one is that they're pretty sensitive to overhead, and they notice that guard evaluation from Dynamo is like 3 to 4% of their throughput. And so they're like, we don't want to evaluate guards, nah. Similarly, they don't want to spend a long time compiling stuff. So the caches have sort of come into being, and they are nice, and I think VLLM definitely would benefit from them. But in the non-cached world, it definitely was a sort of, I only want to compile once. Like, I don't want to be like compiling multiple times, especially for different sizes, because it's going to take forever to warm up in that regime. And finally, they're very interested in like pushing the limits for, the performance, inside of their code. And what that looks like is sort of, hey, I got a bunch of different kernels. I want to make different decisions based on, what size I get. Similar to how like libraries like cuDNN do different things depending on the input shapes. And, when I have a kernel and it's fully static, I would just want to figure out what the optimal launch parameters, like block size and stuff are. So I want to use the best option for any given size. Okay, so there's a number of interesting things that got turned up here. So one of the things is that VLLM currently has their own custom backend, where they're doing a lot of strange things. So one strange thing they're doing is that after Inductor generates some compiled code, they go and they rewrite the bytecode to talk to connect directly to the compiled product. So they just bypass guard evaluation entirely. It's like, Dynamo generates this bytecode that's the compiled thing, jump to it, and then go ahead and run it. They also have this thing where they like, I don't know. they're like sort of feeling their way around the backend extension API to sort of figure out how to not end up compile things multiple times. And so here a little discussion about how Dynamo works is in order, which is that the sort of standard model for how we do size specialization in Dynamo and Inductor is that if you want to do something specifically for some size, then the like easy thing to do is to register a guard, which basically says whether or not the resulting compiled product is valid for that size or not. And if that guard fails, then we'll go ahead and recompile the entire compiled region again the next time. And so in your steady state, in principle, you could have a lot of, compiled codes, one for each configuration of shape you're interested in supporting. Although in practice, you have one or you blew out your cache in a lot of situations. But once you've gotten a compiled product here, there's still some other stuff that happens beyond the Inductor compiler. So if you have CUDA graphs turned on, then the first time I run my compiled function, I'm going to go ahead and run CUDA graphs on it so that I can record a CUDA graph that I can replay again later if I get the same inputs. And in particular, we added this funny thing, just for fun, I guess. I wasn't really sure if it would be useful or not, which is that if like I had a dynamic shapes compiled product, which could work on different sizes. Well, CUDA graphs doesn't work on multiple sizes. So we just, re-CUDA graph for every dynamic size we see. And so you end up with n CUDA graphs for n is the number of distinct sizes you see. One more thing, which is that, so one of the optimizations that the VLLM team was interested in was like getting good launch parameters. So we don't pick the launch parameters for our Trident kernels during inductor compilation. Instead, when you actually try to go run the Trident kernel, that's when we run the auto tuning process and figure out what the launch parameters should be. According to Nicholas Macchioni, we in fact use the very first size we see for the auto tuning config when dynamic shapes are involved. So you better warm up with a good size. So basically, the situation here boils down to this, right? We have this like standard model for doing optimizations, which is I'm in the inductor compiler, I generate new guards, and then I get to do whatever I want, with this new information. Like, so I know it's a multiple of 4. I can completely change everything about all the compilation process that I do, because that's how guards work. Guards let you do something, and then apply it uniformly everywhere. Or you can delay an optimization to runtime. So for kernel selection, this is the easiest version to see, which is that instead of generating a hard-coded call to one specific kernel, you generate a conditional. And the conditional will dispatch to one kernel if the size is X, and another kernel if the size is Y. And so you, quote unquote, inductor compile only once in this case, but you end up with, a little bit of extra runtime overhead to decide which kernel you go to. But the runtime overhead, for example, could be eliminated if you CUDA graphed it, because CUDA graphing would just do the dispatch up front in this case. So we don't really do this runtime post compilation thing very much. It seems like a reasonable thing to support, but yeah, that's sort of one of the reasons why I thought this would be a good topic for this meeting. Questions, comments?
I want to comment that one of their motivations is that, like, if we do the first approach where like inductor specializes on the shape, they actually want to bypass dynamo compilation. Like if inductor specializes on the shape, then the shape guard bubbles up to dynamo. And then like if the shape changes, then like you need to go through another round of dynamo. And they don't want that recompilation.
Kind of related to that point, how reasonable would it be to, like today inductor can do that. Like today inductor can, during inductor compilation, it can guard extra things and lift those guards to dynamo. And not claiming that we should do this, but I guess I'm curious how reasonable it would be to like have an invariant that we never do that. Like anytime inductor were to guard on shapes and like generate different kernels based on those, it would always keep those like inside of some runtime gated thing instead of lift them up to compile time. That seems like work, but it also seems like strictly better in terms of limiting recompiles.
Simon?
Also another point on runtime overhead is at least from like the compiled autograd examples I have of very large graphs with many inputs, like maybe only 2/3 of the total runtime overheads from cache lookup. There's like a third that comes purely from safety checks we have in the inductor codegen, like asserting that the sizes and the strides are what we expect. And even in like our reduced overhead mode, CUDA does a lot of ref checks to make sure that we're not leaking memory between iterations. And these are checks that, yes, they'll give you a pretty nice error message, and they'll just crash the program. So I guess that there seems to be like maybe some value in giving users like a less overhead check mode or no checks mode, and they make sure that their model already works with the checks version.
Driss.
This may be in the doc, but like where does export come into play with this?
That's a good question. They don't know how to use export, but I also he said that Jansel had discussed this topic with them a little bit. It does kind of seem like export might be a useful modality for them. So instead of using torch compile and then having to like bodge the guards, instead you would have some API where you would export the thing you want to inference, but not really export it because they just want to call it from Python and then call that. Yes, Hars.
I was gonna, like I fundamentally I just don't think export fits here because they do not want to move their code out or like export as what it is today. Like they don't want to like have a separate runtime and then a separate graph capture process. Like that's not what they want.
But for example, Horace, would they be willing to like have a UI like sticky cache?
Yeah, like that would be much more along the lines of what they want. Like I mean, like I think people's instincts for exports are reasonable here because there are a decent amount of things that are similar to export. So you can imagine it's like they want explicit control over the guards, they want explicit control over dynamic shape capture, but fundamentally they do not want a separate representation independent of their original Python code. And to me that's like the main difference between do you want export or do you not want export.
Any other comments, questions? Okay, so to kick off some more discussion, I wrote some recommendations for what I think people should do. I want to ask you to tell me if they seem reasonable or not. So, okay, so one is that when they say we want to select kernels based on a specialized size, I think they should do a runtime dispatch in their custom operators. And I think this works. And if they CUDA graph, they don't even have to pay the cost for it. And you know, this is just like very normal. You just have an if statement in your custom op implementation. Does anyone think this is bad or like it doesn't work for the use case?
I'm wondering if like,
okay.
Sorry, go on.
I just say I am worried this isn't sufficient. Like fundamentally, like there are certain transformations you want to do that depend not just on or like aren't just kernel specific, but are more related to like they're like larger transforms that you want to do depending on like their certain graph size. So one immediate example that comes to mind is like, let's say, I think one example they gave is they want to do padding. And so padding is a type of thing that you, like if you do padding on your certain operator, you want the padding to be fused into the previous operator the vast majority of the time. And this is not sufficiently restricted to only a like within kernel optimization. This is something that would need to happen more on the graph level. Another example that comes to mind is like kind of collective related optimizations. So in particular, depending on the range of the collective that they have, they either want to probably use like a low latency collective, or they might want to do more of like a like async TP, like split the reduce scatter and all gather like across the graph, across like the module boundary type optimization. And this does not this is not sufficiently restricted to only within kernel optimization.
Richard.
Okay, I was going to say something similar, which is I think the custom operator like dispatching approach assumes that they already have a kernel. It's like they've written their own kernel, and then they can just pick between different kernels. Like I wonder if they want to just like use inductor to optimize like code for a given batch size and then just dispatch that somehow. And it's harder to get that set up in a custom op case.
Jansel, I'm calling on you. What do you think? Like, how well can inductor support like the sort of bigger runtime selection?
What do you mean by bigger runtime selection?
Well, I mean, well, okay, let's take a specific example. So Horace brought up padding as an example where they want to pad operators and they want to fuse the padding into the previous operator, but they don't want to like generate guards. So you still only want to compile once for all the sizes that you might want to pad to.
Yeah, I mean, like for this stuff, I tend to think like this is a use case that like AOT inductor type workflows should be able to handle really well. Like maybe it's not the existing export workflow. I think the existing export workflow is a little bit wrong for this.
Well, tell us what the export workflow looks like in your ideal world.
I mean, I think there's a like a lot of people come to us and say like oh like compile time's a problem, right? Or like maybe you're like in like an inference server and you know, there's like a web request we're waiting, and like you can't take like a, you know, few seconds spike in latency if you know, guards fail. Like having a way to ahead of time compile a PyTorch model and have a hard guarantee that like there'll be no further compilation after you call this Python API, I think would uh, solve a lot of the compile time problems especially like in like low latency environments where you have hard latency guarantees.
So concretely, like if the way you did this would be like, sorry, if in eager mode you would end up with say 8 compiled products, then that would be fine. Like that would be very reasonable in your book here.
Yeah, you could potentially have multiple compiled products. You know, like maybe it's the case that we like find a way to have no guards at all. Like we could say, you know, like the user could provide sort of guarantees that certain invariants are kept. Another way to do it would be to keep the guards, but if the guards fail, just fall back to eager. Like this is sort of like the equivalent of the run mode, which we already have. But the you know, like the basic idea of saying like having like a line in your Python program that says like please precompile, you know, with a bunch of options, and then like after you use that API have sort of a guarantee that there's no further compiles. I think is like the like more of the API that might help here.
Or I guess I disagree that this is what export is for, in the sense that like what they want here is like explicit control over the compilation artifact. And I kind of view this as pretty different from like what export is intended for, which is a independent representation of their like the independent representation of their PyTorch model.
Yeah, I specifically said AOT inductor, not export. Like I think I agree with you that there's like this export, like leave the PyTorch ecosystem. But like I think for AOT inductor, you should be able to use AOT inductor in a way that just controls when things get compiled.
Or I guess maybe I don't really even understand why this is like AOT inductor related, right? Because it, like most of like the like recompilation or like not recompilation part stuff is not about like they want to avoid Triton compilation. It's more like happening at the Dynamo layer, if anything. Like as in like to me like this like I guess your point just feels like a general.
Are we just talking about naming? I don't. I think like we can call it whatever. You can pick the name.
Let me try to put a point on Jansel's point, which is that the regime Jansel is calling for is like not a lot. It's like very little work, right? So basically, we go to VLLM and we would say, hey, you know, compile it X times, where X is all the distinct size configurations you care about, and then we'll bundle it all together, and then you know you'll have fast startup because it's all compiled already. And are you happy with this?
I think to me the question like or like I think to me the distinction about like AOT inductor versus torch compile is that like is this viewed as like a like an API to torch compile, or is this viewed as like a like
well, let's say it's an API to torch compile, right? But you have control, but the control is mostly like, yeah, I'm going to generate 16 copies of the compiled code for various situations, and I will guarantee you that you know you'll hit cache at them.
Okay, we're doing I think it's reasonable. I think the other question I wanted Jason's opinion on is that like related to how the dynamic shape control in this world would interact with the compiler. Because specifically, right, like the way that these shape guards typically work today is they are kind of like bottom up. Like the shape constraints are happening in inductor, and then they bubble up to the front end, like you know the recompilation system. Like, is this correct? Like, or you can imagine another way the system works is the recompilation is directed by the user, and then the compiler just simply respects all of those constraints.
So like this approach to dynamic shapes is something that we did previously work on in sort of export, where the idea is like when you're exporting something, you'd get sort of like this guards object, that guard and like basically the user would have to make some sort of promises which allow you to sort of statically prove that the shape guards are valid. So we could do sort of that like like that type of the type of thing. Another thing we could do is we could like I could imagine something you want to do would be have like support for many different shapes, and then have like a runtime switch statement where you have like specialized kernels, and that's something where like the guard mechanism can kind of do that, but it's like not really as fine grained as we might want, because like you don't really need to recompile the entire model if you only need like one kernel to be different. So you can imagine sort of like more low level or more like kernel by kernel sort of type switch statements for shape guards. I agree that like for I think sort of like a different contract, where where we have more sort of a more top-down control of guards. Like specifically, I feel like if I feel like a thing that you might want is the user could specify like, oh, like my model is dynamic in X, Y, D, Z dimensions, and then have a way that where like we guarantee that we either won't guard on those dynamic dimensions, or if we do need like some specialization, we'll like generate multiple kernels and we'll switch dynamically at runtime.
I think one worry I have, generally speaking, is like, is this the right way to do it? Because one thing I worry about, right, is like we have some heuristics in our compiler that look stuff like, if sequence length is like less than 1024, do blah, otherwise do foo. And so if you think of this from the perspective of the user, how do they even know like what decisions the compiler is going to make? So like let's say you say or like let's say the compiler has a threshold of like less than 8 and like more than 8. And then you set the threshold at like 6. This does not like if you then compile like or basically if like the ranges that you are trying to compile with from the user perspective do not align with the like thresholds from the compiler perspective, this seems kind of like you lose something. Like it's like you lose like some of like the recompilation benefits. Like you lose ability to specialize, and so like it's I'm not super certain like what's even the right way to do these kinds of optimizations.
I mean, for some of these optimizations, it makes sense to just turn them off. Like for example, like if you do like a reduction of size 5, we just unroll the reduction and we actually don't even do a reduction. We just do like 5 statements added together, and like that type of thing. In the dynamic case, we should probably just turn off
Or I'm actually unconvinced by that example in particular, because I actually like the reduction as pointwise actually does enable like certain kinds of fusions that we wouldn't be able to do otherwise. And so like and I guess a specific case I'm imagining here, right, is like for example for like the like transformer inference, it's like for gem Vs. And even for like matrix multipliers where batch size is up to like 2 or 3, Inductor can generate like very good like kernels kind of like from scratch. But then above that, you're unable to do it. And like this is the type of optimization that I do think they would want. Like they would probably want special kernels for like batch size 1, batch size 2. Yeah.
But I guess as you mentioned, like the fusion effects can sort of ripple throughout the model, so it's like really hard to contain that. So are you proposing we just like compile the model for like a large number of sizes, like maybe like all powers of 2, and then have like a giant switch statement, or like what's your proposed solution there?
Or I think the like I'm just uncertain about like whether like bottom up or top down is like a better way to like control dynamic shapes generally, because from the user, like the way it works today is like bottom up, and this is like very nice from the perspective of the compiler control, because regardless of like if we decide that like we're like okay, like every time it comes to a decision where we can shape specialize or not, we can make the decision that, oh, if this is dynamic, then we like always like if this not important, then we just always choose like the generic option. If it is important, we can like bubble up this decision to the to Dynamo and then ask for a recompile like if the shape changes. Like for example, I think there's a bunch of cases where we specialize on like, is this number like divisible by 16 or not? And that's like not the type of thing that you necessarily have the control over if it's coming from top down, where like the user needs to specify all of the shape constraints and then potentially needs to play like whack-a-mole about like which optimizations do I want to trigger in the compiler that require like certain preconditions to happen.
We're over time, but I want to butt in actually, because to me it seems like there's no way around like the compiler has to like make decisions about when optimizations apply or not. So it seems to me that like in the limit, you need some collaborative process, right? Where, you know, the compiler's like, well, here are all the splits that I could do in the dynamic size space, which, you know, control various optimizations I do. And the user has to like make a call like, yeah, generate all, you know, 100 configurations for every single possible difference or not. Or, you know, actually I don't want to do those. Like these are the only ones I want. But like it doesn't seem to me that there's any way to like set things up so the user is just completely oblivious to like what size specializing optimizations the compiler has.
I agree with that, and the fundamental reason is it's not even worse than 100. The problem is that with combinatorial explosion, it's exponential, and so like you can start specializing on things, and specializing can bring speed ups, but if you specialize on all possible combinations, then you get exponential explosions.
Okay, we're out of time. Thanks everyone.